Hello there, nice little topic for us now on exercise 4a, looking at sequences. And of course we did a lot of sequences back in GCSE time, so this should be fairly straightforward, I hope. And you notice the slide there has a picture of a sunflower seed. Now it's said that the Fibonacci sequence, you might remember this phrase, the Fibonacci sequence, determines the arrangements of this and how many of these seeds are in each of these kind of diagonals. Well, they're not really diagonals, are they? It gets hard to count after a while, but you can see they are kind of formed like that. And I'm told you can, I say I'm told because whenever I look at it I'm never quite convinced, but you can certainly see there's arrangements here of the seeds, and you can, I mean, the Fibonacci sequence, by the way, you should recall that is 1, 1, 2, and 1 and 1 make 2, and then 1 and 2 make 3, and 2 and 3 make 5, and 3 and 5 make 8, and you just add up the previous two terms, 5 and 8 make 13, and I don't know, see if you can count those number of seeds in there. It might be that you can work out why, and perhaps go away and look up on Google or Wikipedia or something about Fibonacci sequences and sunflower seeds. The argument is that the Fibonacci sequence occurs lots of time in real life, in nature. The typical example is the population growth of rabbits, but it doesn't have to just be that. Go and have a look. There's meant to be lots and lots of different situations where this applies, and that'd be a nice little project for you to go and have a look at where Fibonacci sequence crops up naturally in the real world. But nevertheless, this is one I was talking about, 1, 1, 2, 3, 5, and now we've seen it. The next ones would be 8, 13, 21. As I say, what you do is you add two terms to get the next term. This is the Fibonacci sequence, of course. Now, the general term of a sequence, can you find the nth term of these? This is something you should be fairly good at. 2, 4, 6, 8. Well, I hope you're thinking 10. Now, the fact it's going up in 2s, of course, is the critical thing. And as soon as I see it's going up in 2s, I write 2n. Now, 2n is actually the 2 times table. And this is the 2 times table, 2, 4, 6, 8. So that is actually the nth term. 2n, there you go. Now, some of them are less obvious. Well, this is a fraction, but other than that, on the first term it's 1, but on the second time it's 1 over 2. The third time it's 1 over 3. I think this is just 1 over n. Yeah, 1 over n, there it is. Next one, what's this? Well, this is starting to get a bit harder. Apart from, I'm looking at 981 and 729, I'm thinking 3s. I know 3 to the naught is 1. I know 3 squared is 9. Oh, I've got a minus there. I know 3 cubed is 81. No, it's not. 3 cubed is 27. Ah, right. So we've got something slightly weird going on here. And 3, well, that's 3 to the 4 then is 81. And here's what's happening. We're just timesing by 9 each time. Well, nearly, aren't we? We're nearly doing that. I thought it was going to be a powers thing. But we're just timesing, I think, by 9 each time. But it's changing sign as well, so I suppose we're timesing by minus 9 each time. Minus 9 times that will give me minus 729. So it times in the last answer every time by that. Now, just notice what the answer is. Minus 9 to this power. So I was expecting this to be 3. This is what I was expecting the answer to be. 3 to the power of something. Turned out it was minus 9 to the power of something. Notice the power is actually n minus 1, because this is 9 to the 0 is 1. Well, they're saying, well, minus 9 to the 0 is also 1. And minus 9 to the 1 is minus 9. Minus 9 to the 2 is 81. And minus 9 to the 3 is minus 729. Notice, on the fourth term, we've had to do minus 9 to the 3, so that the fourth term is to the power of 3. That's why it's to the power of n minus 1 here. And The final little warm-up question, find the first three terms for this sequence. Well, this is the other way around, isn't it? You can see they've given me the formula. And they say first three terms. Well, all right then. I'll say n equals 1. If I put 1 into there, I get u1 equals 5 plus 2 times 1 squared. Well, I reckon that's 7. When n is 2, u2 will be 5 plus 2 times 2 squared. Well, that's 13, I think. N equals 3, the last term they want. So it's 5 plus 2 times 3 squared. 3 squared is 9, times 2 is 18. I reckon that's 23. Don't know what the answers are. 7, 13, 23. Actually, it then gave me 2 more, and you said the first 3 terms. So that's what I want you to do now. The first one is a bit like the one we just did. Write out the first, here it does want the first 5 terms of these 4 sequences, and you can just type them in. So take this one here, B. If I want, well, you're going to have to find U1, U2, U3, U4 and U5 for each of these. But say I wanted to do U5, I would do minus 2 to the power of 5. If you do that on your calculator, you get negative 32. Do that for all of them, 5 terms for each. And then also, I want the general term for these. So some will be obvious, some will be less obvious. So I will pause the video if I was you, give yourself some time, and then restart the video. It will take you a good 5 minutes, I reckon, to do that. Okay. Well, I can put the answer up, that's no problem. But what I was also going to say is, some of these are a little less obvious. I mean, certainly, I think these ones you should have got fairly straightforwardly, because you just put them into a formula. I suppose these ones you might have struggled with, because they're not necessarily, like this one I think similar to the one we just did, but it's still tricky. How do you write this? I suppose some of this is not knowing how to write the answer. So in a bit, when you see the answer, write down the answer and then try and get your head around the answer. Let's go through them. These are my answers. So my first one, it says 1 minus 4n, so my first one is 1 minus 4 1s, which is minus 3. 1 minus 4 2s, minus 7. So these are the right answers. So remember what you're doing is, for u1 there, you were doing 1 minus 4 times 1. For u5, you do 1 minus 4 times 5. You just type into your calculator. The second one, it's minus 2 to the n. So you do minus 2 to the 1, minus 2 to the 2, etc., etc. And this is what I would get when I do it. Now, you've got to be a bit careful on this. So in this, say u2, you might have got the answer of minus 4. But that's because you needed to put it in brackets. Minus 2 to the power of 2, for instance. And that will give you 4. But if you don't remember to put the brackets, you'll get the wrong answer. Next one. Here they are, 2, 8. I reckon you're probably more likely to have got that right. And the last one, very similar to B, I would imagine. But now all the answers are 1 and minus 1, alternating between the two. Give the general term of these sequences where they're going up in 2s. So you should remember this from GCSE. The 2 times table, which is 2n, is 2, 4, 6, 8. So you notice I don't want 6, I want 5. I don't want 8, I want 7. So I have to take away 1. So that's my answer, 2n minus 1. Next one, 1, 4, 9, 16, 25. Well, you either recognize this or you don't. These are what we call the square numbers. So un equals n squared. Notice this, 1, 4, 9, 16, 25. Look out for them. This is like the one we just saw. And I think this one's not far off, but you say, oh, that's a complicated one, isn't it? Notice I've written that a bit mean. There's better ways of writing that. But write it down, then we can talk about it in class. Okay. Recurrence relations. We've already seen how do you write the nth term of a sequence. 3, 5, 7, 9. It's going up in 2s. But the 2n, which I want to write, is 2, 4, 6, 8. So we have to add 1 on. So 2n plus 1 gets me the right answer. So that's the nth term. Right? And when you write this, it says un equals, and you'll notice on the right hand side is n, with some kind of rule to do with it. So it might be n squared. In this case, it's 2n plus 1. However, there is this alternative way of thinking about this, and it comes back to the idea that you look at this and you go, oh, it goes up in 2s. Each time it goes up in 2s, goes up in 2s, goes up in 2s. And you can write that as what we call a recurrence relation. And this is the recurrence relation. And it basically means that And look, notice first of all it says un plus 1 equals um then plus 2. So it's, and this is a little n plus 1, whereas this is a proper big old plus 2, a proper plus 2. Not, so the plus 2 isn't next to the n there. And what's it mean? Well, it basically means in order to find the next term, which I'm calling un plus 1, we take the last term that we had, which I'm calling un, plus 2. Now, if you like, I'm saying u3, for instance, equals u2 plus 2. I'm saying u12 will be u11 plus 2. Notice in each case, if this is 2, this is 3, if this is 11, this is 12, the next term is always one more than the last term. So if I know what u2 is, well, I do, it's 5. So equals 5 plus 2 equals 7. Now the drawback of this method is, unless you know what the 11th term is, you can't work out the 12th term. So that's why it's a bit, but it's not as useful, I would say. And these are called, though, recurrence relations. Let's do a recurrence relation. Well, they tell us u1 equals 5, and they give me my formula. My formula says un plus 1, my next term, will be 2 lots of my last term, take away 3. So let's do this. u2 equals 2 times u1. What was u1? It was 5. Take away 3. So that's 10, take away 3 is 7. Now u3 will be, I'll do the same trick, 2 times my last term, 7. Take away 3. That's 4, that's 11. What's u4? It says 2 times my last term, 2 times 11. Take away 3. So that's 22, that's 19. And it says my terms are 5, which they told me already, and then 7, 11, 19. Yeah, that's what I got. There is an easier way to do this. I'll perhaps show you this in class. We can do this quite quickly on our calculator and using the answer button. So this is something which perhaps you need to remind me of, and I'll go through this in class, how to use that answer button, which is here, to do these. Give the first term and write down a recurrence relation for this. Well, what's happening each time? Well, just look at it. You know what? I'm just timesing by minus 4. 1 times minus 4 gives me minus 4. Times that by minus 4, I get 16. Yeah, that's working. Times by minus 4. So what's my, well, my un plus 1 equals my last term times negative 4. Now, I could write it like that. To be honest, it's better written as un plus 1 equals minus 4 times by un. And that's the answer. What have we got? Oh, I should have given as well u1 equals 1. Yeah, that's what I got. You always need, on a recurrence relation, to say what the starting point. Otherwise, you'd never know how to do it. So unless I've got a point, I can't find the next point. So that's why it's important to give the first term. A few terms we need to know. You need to understand what is meant by the following words. I've written them all up here. Look, periodic, a repeating pattern. 5, 8, 15, 5, 8, 15, 5, 8, 15. Increasing, they keep on going up. Decreasing, they keep on going down. Converging means they get closer and closer to some number. Look, 2.4, 2.45, 2.478, 2.492. Now, they seem to be getting closer and closer to 2.5. I can't read it very well, blue on blue. But that's what they're getting closer to. So it seems to be converging to this number 2.5. Diverging, it definitely isn't getting closer to anything. Look, 3, 4, 8, 7, 6. These are getting miles and miles and miles apart. So that would be called converging. Last question here. Write down the values of u1, u2. Your u1 equals 6. Tells me that in the question. u2, it says 2/3 of that, which is 4, plus 5 is 9. u3, 2/3 of 9 is 6, plus 5 is 11. And by setting up an equation, find the limit. Well, the limit implies that, look, this we pretend is the same thing. So L equals 2/3 of L plus 5 times everything by 3. 3L equals 2L plus 15. Move that over. L equals 15. Look at that, I solved it. That's something we definitely need to practice in class, because I don't reckon one example is not enough on that. Look, in class then, we are going to do exercise 4A. Thank you very much.